sometimes the big one will eat the little one. Sometimes they just, like hang out for a bit, and sometimes they kind of get bored of each other and wander off. Actually, that's less common than for them to hang out, almost as social groups. Just want to stress, these do not have any DNA. All this complex, oh no, right, sorry, just stop that for a second. This is my favourite movie in the whole world. What we've got is one group of protocells here, all hanging out, having a good time, producing a little bit of skin. Here, we've got a second group, the away team, okay? And so they're coming out to check the home crowd here. Watch what happens next. I don't think we can actually explain this in very simple physical terms. There is no DNA. That is a chemical solution provided by complex chemistry that is not predictable through simple computer modelling. I mean, the research groups that I work have got computer simulations of some of these protocells, but we weren't able to anticipate that. That's not a one-off either. I've got numbers of those. Let's just get excited about it. So essentially, no DNA. And what you're getting is a lack of determinism in morphology, and yet a great deal of sensitivity to minuscule variations that's going on in that oil field. I mean, seriously, this is all within the space of about 5 centimetres. And so all these variations in performance and morphology are created through environmental changes, and that's so I think that's the key point, because that's what I'm going to talk about next. This is my second favourite part or a movie of all time. What I did briefly say that there are some kind of homologies between protocells and biological systems. These are protocell roses. I have no idea how that happened, but I was just lucky enough to catch it whilst it did. So the idea is then that there's this whole set of terminologies that's emerging around these living technologies. Artificial biology is something else that's being applied to bottom-up synthetic biology because of its lack of it's not that it's not engaged with DNA, because we've got groups like Shostaks that are taking the idea of a minimal cell, starting with this oil and water droplet system, and then trying to introduce this model system which relies on the creation of a membrane or a container, the creation of information, which is RNA or DNA, and a metabolism of some description. Many of them are based in the membranes around these cells. And what's neat about protocells is they're all turned inside out. So rather than all the organelles kind of being sitting on the inside, staying away from the water phase, protocells have their metabolisms on the outside. They kind of wear their metabolism. So when you give them artificial receptors, it's all happening at the interface. And so kind of the notion of interface is really key to this kind of idea of bottom-up synthetic biology or artificial biology. And so what was kind of striking about the systems that we're working with is that we actually have a way of sensing and engaging with environmental changes. And so if you remember back to the Darwin's theory of on the origins of species, and the notion of natural selection, there are two components to evolution. And since the 50s, say, we've really focused on directing evolution through the body. And I think, kind of politically as well as culturally, we're at a time where, we need to kind of get re-engaged with technologies of the environment as well. And the way that I'm thinking about the living technology or these kind of bottom-up synthetic biologies is to use them to influence microenvironments by thinking of them a little bit like environmental pharmaceuticals. Now, we're used to the idea of restoring balances within bodies by introducing, some of the drugs that were being talked about earlier. And that allows a kind of a reharmonizing or a kind of a buying of time, whilst complex systems and complex processes essentially re-establish connections under these new set of environmental conditions. And so we're thinking about these protocells as being almost like little slow-release containers that in the next 10 years these protocells are thought to be able to reproduce themselves. We can chemically fuse them, and we can chemically cause them to divide, so we can induce cell cycles. And we've got protocell groups around the world that are trying to introduce RNA and DNA. But I mean, for me, that's kind of, it feels wrong. It feels like trying to bring a Cartesian notion of order back into something that's inherently complex. So I would be much more interested in finding out what these systems want as a form of chemical organisational matrix or information-based system. I don't really want to throw DNA in there and then expect it to work. So the bottom-up approach appeals to me. So what is the information system? Well, essentially, because it's got no DNA, any chemistry. And so what we've been doing is we've been putting essentially very simple inorganic chemistry inside these little balls of fat and asking them to do very simple calculations. So these ones can produce carbonate from dissolved carbon dioxide in water, and so that can make little fatty-looking protocells. Now, but the thing about this is, okay, it's very early. It's a very early stage of development. We're talking to people about developing pain space within the system. But what I find interesting about this as a principle is that here we have a technology that can produce a material that has biological-like properties. It's not biology. We're not hacking into existing biological systems. They are biological-like. They have a greater solution space than biology does. They also have, and there are advantages and disadvantages in that. And so the question is, how can we apply them? And so where my attention has been, I said I've been interested in environmental influences. I've been trying to think of ways in which I could use these protocells to metabolize carbon dioxide and take it into the context of the built environment and to use it as a building material. Now, what's neat about architecture is that, in my view, architecture is an environmental technology. It's a technology of environments. We've developed our architecture so that it keeps the homeostasis, which we find comfortable around us, so nice warm environments, we've got air conditioning, we've got insulation, everything's focused on the inside. What we haven't done in architecture is turn that technological interface outwards and looked at how we can actually generate architectures that have a technological engagement with the environment. Now, like I say, the scale that these are at, and I think scale is something very interesting. I think Max was kind of talking about that with the singularity at the beginning. And there's kind of a notion, I think it's TO something rather. Philip Beasley sent it to me the other day. It's about the notion that scalar isn't necessarily the same as linear. That when you scale up systems, they don't necessarily make these transitional jumps in a linear way. So, for example, the human body is an absolute kind of an example of that. That you have tissues, like blood, that are bigger than organs, say like the eye. And so that just because something's a particular size doesn't mean that it's inherently going to have a particular order associated with it. And this order's patchy. If you think of all the different kinds of tissues in your body and all the kinds of different levels of organisation and association, this kind of notion of how scale relates to function and the kind of the observed consequences of that is much more exciting than I think the traditional engineering way of looking at materials, scale, function, chemistry is talking about it. So thinking about using the entire interface between architecture and the environment as being a way through which we can now start to direct microclimates first of all, then urban environments, urban contexts, use these kinds of dynamic material systems to clean up pollution, maybe replenish air within a dirty urban street and take out carbon dioxide and change it with oxygen. But really we're working with groups as well that